The 2 hours is too short to give, proper lectures on actions. So I'm gonna sketch some important properties of actions. Meaning, basically, I am telling you the stories about actions. So mostly, I follow the lines of Pechai, the first reference. So here, I find it very useful to understand grand picture of action physics. And then, of course, recently action became, kind of a trend. So there appeared many review papers. And then probably one of the classic report made by Kim and Karoji, 2008, or a long time back. And then the other three references should be more relevant for the lecture by Professor Takahashi. So it contains all the new developments. So about, astrophysics, cosmological aspects, and then some flavor issues, etc. So you can learn more about this. So basically, I am following Pechai and Kim and Karoji. So today I will start with the U1A problem, and then from which we understood what the QCD vacuum should be like. And then this leads to strong CP problem. And then Pechai Quinn suggests to solve this problem nicely. So that will be the content of the second lecture. So 1 hour each. So I don't know, okay, so we will see how it goes. Okay, so U1A problem. So, this is QCD Lagrangian, everybody knows, right? So G is gluon field strengths, and then we have left-hand, right-handed quarks. Of course, QCD is strong force doesn't distinguish between left-handed, right-handed. But it is, for us, the electric theory is chiral, so this distinction will be relevant for our discussion later. And then the mass, M here, let's just take a diagonal masses, MU, MDMS, the 6 quark real positive masses. So I wrote M and Dega formally, but taking real positive, it has no meaning of taking Dega here. But anyway, so since the real have some phase effect in the mass, so I just keep track of M and M Dega. So we know, the QCD condensate below around 1 GeV, which is the proton mass scale. So that in this case, the UDS quarks are massless, basically. Their masses are much smaller than 1 GeV. So we can treat UDS as a massless particles. And then in this limit, there appears pseudo-Nambu-Stone boson like mesons. So we know the chiral-perturbation theory describing the dynamics of these hadrons in terms of effective Lagrangian. So I'll slightly touch upon some of these equations. So okay, so taking massless quarks MU, MDMS going to 0. You see, the left-handed quark and right-handed quarks can rotate away independently, right? So we have the left-handed rotation and right-handed rotation for the 3 quarks, which is symmetry of the Lagrangian. So this is called U3L cross U3R symmetry. And then the diagonal one, so the left-handed rotation and right-handed, if the left-handed rotation and right-handed rotation is the same, so we call it diagonal or U3V. So then the U1 part is just a baryon number we know of. And then SU3, it's a good symmetry. Both of them is good symmetry, the standard model, baryon number is a good symmetry. SU3 vector is also good symmetry. So basically isospin, the operator of this, we know that this is isospin and S strangeness. So imagine the Pseudo-Goldstone boson in the meson matrix, we have octet like this. And then we would expect to have Goldstone boson corresponding to U1V. No, sorry, no, this is not. Okay, so this is a good symmetry describing, isospin and strangeness and then baryon number. Now the U3A, we take the opposite rotation. I mean, different rotation of L and left-handed and right-handed quarks. Then also again decomposing it to SU3A and then U1A. So the meson, this meson octet, okay, yeah, perhaps you know that this is I3 direction, this is strangeness direction, right? So meson octet is basically Nambu-Goldstone boson, which to be massless for mu, md, ms going to 0. Because, I mean, this is spontaneously broken by the quark condensate. Also explicitly broken by the mass, non-vanishing masses, mu, md, ms, which is small. Now the U1A, so there is the candidate of this U1A Goldstone boson, which is eta prime. Now, we know that this pion, kaon, eta meson masses are much below the 1 GeV, the ionization scale. But eta prime mass is around 1 GeV. So why? I mean, this doesn't sound like a Goldstone boson. So actually, people were wondering about this. And then from basically chiral perturbation theory, okay, so we can explain the masses of pion, kaon, and eta in terms of this kind of relations. So I will show more explicit expression for this. But taking some chiral perturbation, some constant b. So this mass is determined by b, some number b times for m pi, the pion is mu plus md, and then for kaon, ms times b, and then eta is also ms times b, roughly speaking. So these masses are quite well explained in terms of this Pseudo-Goldstone boson nature, Pseudo-Nambu-Goldstone boson nature of meson octets. But eta prime, we cannot explain this. Eta prime also contains U, D, and S quarks. Actually, this is a singlet. It's a combination like a U bar plus DD bar plus SS bar. So somehow following this rule, I mean, we would expect that the eta prime mass should be some coefficient times ms times b. But we don't find any way to explain the eta prime mass in this way. So yeah, it is large, but it can be explained. MS is much larger than mu. So yeah, in this is master key. So having this B parameter is called what? A back parameter, about which is around 400 GeV. So the pion, eta, k masses are explained in this way, in a single formulation, but not eta prime. Okay, good. I mean, please tell me whenever you have any doubts or questions. Otherwise, my sketch would be too short. Okay, now here comes the story of chiral anomaly. So what we understand now is that actually U1A is not symmetry. It's anomalous. It has a kind of anomaly, meaning that it's not a symmetry. It's a symmetry at the classical level, but it's not a symmetry at quantum level. That means axial vector current is not conserved. So axial vector current, you take a derivative then using equation of motion, you get this relation. So since we are taking the massless quark limit, this should vanish, meaning conserved chiral current, axial vector current. But this turns out to be non-zero. So actually, this was the solution understanding why pi zero should decay to 2 photons, right? I mean, this is, you can, so if you didn't study before, so please read the Paskin. I mean, all the quantum field theory book have explanation of this. So I skip the details. So please go to this book. And then at the end of the day, okay, so this derivative, after taking some regularization properly, so you will get this non-trivial contribution, which is called anomaly term. So this is a homework to derive this equation, right? So I'm talking about only easy part. So difficult part you should do yourself, right? Or at least, yeah, you can just look at to understand how the story goes. So, so long time back, actually, Fujika gave a lecture on anomalies in one of our summer school. So you can go to this KIAS webpage to get his lecture notes. So he calculates this triangle diagram using, you know, this is this kind of diagonalization. What is it called? And then, yeah, I mean, so you can find explicit calculation to get this non-vanishing contribution like this. Okay, so actually in the beginning, in chiral perturbation effective theory of QCD, so we can write down the pion and nucleon interaction like this. So this is a pseudoscalar, so it has a pseudoscalar interaction with nucleons. So pion can couple to 2 photons with the protons in the loop. So if you calculate this and then you get this decay rate. So I mean, this is just this is a pion decay constant, which is 93 MeV, and GA was 1.2 or 3. It was determined like that. So people were able to calculate this decay rate like this. And then, yeah, if you look at this, then, okay, so all the 4 pi factors alpha, and then all comes from this. This is like alpha over 4 pi. Okay, so the dimension is right. You can get the right phase space factor, etc. And then using this formula, you get GA squared here. But later, I mean, people realize that using in a more proper way, actually, you have to take a GA to be 1 for this anomaly diagram calculation. So the story is written in by Peshkin, the QFT book of Peshkin. So you can go to this reference for the details. So the thing we have to remember is that the axial vector current is not conserved. There is non-vanishing contribution like this FF called FF dual term. And then, okay, so I mean, this is for photon coupling, but for the quarks, also gluon should have the same property. So GA, you know, is octet of SU3. So A is the SU3 indices, octet indices. And then, okay, here you have, say, NF is the number of fermions in the loop. So in the standard model, we have 6 quarks, right? So NF must be 3. As 6. Oh, I'm afraid this may be wrong. This is or this may be 2NG or just NF or 2NF. I mean, factor 2 is really tricky. So please also understand that there must be some uncertainties. Plus minus 2 equals to plus minus pi, etc. So now there comes another story. So if you look at more closely, then GG dual term is actually total derivative, right? So so this expression you can write down in terms of the K vector defined like this. Now, so if you take the chiral rotation in your Lagrangian, then, I mean, you know, according to Noether theorem, you would get this chiral current divergence. And then symmetry, I mean, the conserved current, meaning that this should vanish, right? But having the total derivative, we can take this volume integral to surface integral, and then you go to the infinity surface. Then at the boundary, usually you assume that all the field vanishes. So taking this trivial boundary condition, and this goes to 0. Then again, should this mean that this current is conserved? So there is no U1A problem. Then it's this a bit difficult to understand why eta prime is so heavy. So this question was solved by understanding non-trivial. The QCD vacuum should be non-trivial. I mean, Toft actually realized this, and then which means I mean, okay. So the story goes as follows. So at the infinity boundary, instead of trivial boundary condition like this, we can take non-vanishing the gauge field configuration. So even though this is non-vanishing, of course, you can get the field strength should vanish. So I mean, this you can immediately realize that, okay, so you know that usual gauge transformation, A going to A prime by some gauge transformation U. So A transforms like this, and then the field strength itself transforms like this, right? So now if you take the initial gauge field as a pure gauge configuration, this can be non-vanishing, but field strength can vanish at the boundary. So in fact, in taking SU2, we can get explicit expression of this non-trivial configuration A mu. So in terms of, okay, so SU2 notation, we have a Pauli matrix, sigma A, and then 3 gauge fields. So then, okay, so we know what the Pauli matrices are. So then, okay, so the field strengths, you calculate like this, and then K mu has this expression. And then let's take A mu like this, with this specific form of U1, the pure gauge transformation matrix. So we work in, of course, the imaginary time. So X4 is nothing but ICT or IX0. So here now taking this, you try to calculate this quantity at the boundary, and then taking infinity surface, three surface of 4-dimensional volume. Just you plug in this expression, and then do the integration, and then you will get this constant factor. This is the homework 2. I mean, this is trivial calculation, right? Though I needed a lot of time to confirm all the coefficient correct. Okay, yeah, so now the chiral current, we proved that shouldn't be conserved. So there is this non-vanishing factor. So with this normalization, if we have this non-trivial gauge configuration, which is non-vanishing at the infinite boundary, then this integration is 1. I mean, this is called winding number of the gauge configuration. You know, fancy mathematical term. I mean, so our boundary is superior, S3, and then SU2 is called isomorphic to S3. So it's like the superior going to, I mean, this mapping of superior to superior. So depending on how many times you wrap it up, so we have just a winding number like this. So this is, you know, I mean, this gauge configuration does this stuff. So it picks up the non-trivial gauge configuration with picking up so-called this topological number. Now, realizing this, I mean, so now you take another gauge transformation of this A mu1, and then say, okay, so the n vacuum configuration, so you take un to be u1 to the n. Then it's kind of obvious that so you will get winding number n, right? Is it trivial, right? But it may be not. So you just prove it. So I mean, okay, so you know, in mathematics we use recurrence relation or whatever, and then so starting from A mu n configuration, you go to so-called A mu n plus 1 configuration, taking this gauge transformation and show that this, I mean, just to show this. Then, so A mu n plus 1, for this, instead of un, you get you replace this by un plus 1. So now this, you know, we have this n, the non-trivial gauge configuration having different winding number n. So now, and all of them has vanishing energy density. So each n should be a vacuum state. But this, if you take n as your proper vacuum, then you take a U1 gauge transformation, and then the winding number changes. So one vacuum state go to another vacuum state by gauge transformation, which means that it's not invariant under gauge transformation. So SU3, the vacuum doesn't respect SU3 gauge transformation. So this kind of gauge transformation is called large gauge transformation. But there is a clever way to make a gauge invariant vacuum, which is called a theta vacuum. So you just take a linear combination of this n vector with such a specific phase. Then take a gauge transformation of u, and then this number goes to, yeah, then this vacuum goes to the same vacuum with unphysical phase in front of it. So this can be removed, right? So the theta vacuum is gauge invariant. So so QCD vacuum should be trivial. I mean, should we take the trivial gauge configuration with n equals 1 as a proper vacuum, or should we take theta vacuum as a proper vacuum? So which one do you like? So if we take this theta vacuum as a true vacuum, which turns out to be gauge invariant, and then very interesting stories now comes around. So now our vacuum is a theta vacuum. So you take this this matrix element of our true vacuum. Then after some calculation, you will get this kind of expression. And then this is equivalent to add so-called theta term in the Lagrangian. So path integration, we know that this transition from n to n plus nu vacuum, we take the so-called winding number nu gauge field, integration of all the nu, and then and then in the Lagrangian, if you have this, if you add this theta term like this, then this will pick up a winding number nu, right? So this will give this phase. So living in theta vacuum, meaning that in the QCD Lagrangian, this theta term can be added, should be added. And then this theta is arbitrary number, which can be order 1, it's 100,000 thetas, it cannot be 1,000. Can be 1,000. Well, anyway, arbitrary number, which should be, which turns out to be very, very small at the end. So this caused the so-called strong CP problem. So now it's right time to stop, right? Okay, so the strong CP problem and then Petrarchy mechanism we'll talk about tomorrow. Questions? Ne? Is that right? It's a 1.5 hour lecture? I thought it's a 1 hour lecture, no? Oh, sorry. Okay, sorry. I started at 3:30. Oh my gosh. I made a too short sketch. Please ask questions. So everything's clear, right? Yeah, of course, except the homeworks. Okay, so if there are no questions, let me proceed. I thought that it would take much more time. So now our QCD Lagrangian should include this additional theta term. And then actually, okay, so let us look at this mathematics more closely. We know that this Fourier matrix comes from the electroweak symmetry breaking. Yeah, basically we write down, say, quark doublet, left-handed Higgs, and then U R Y, this 3x3 matrix, plus Hermitian conjugate, and then quark doublet H tilde dr plus Hermitian conjugate. So this YU and the YD mass matrices. So in general, this YU, YD are 3x3 complex matrices. And then actually this, after diagonalization of quark masses, we can pick up non-trivial phase. So meaning that this has, if this has phase I phi, this has phase minus I phi. So left-handed, right-handed quarks behaves differently. They pick up different the opposite phases, and then this phase can be rotated away, right? By this chiral rotation. So to remove this, you take this rotation. Okay. And then we know that this is a U1A anomalous transformation. So that this will change theta vacuum, the theta value to 5 times number of quarks, NF. So now we have 6 quarks. So this 5 times 6. Theta goes to 5 times 6. So removing all the phase degrees of freedom appearing in general quark mass matrices. So the effective theta value is called theta bar, which is linear combination of the original theta plus the phases in the quark field. So basically, you know, I mean, initial theta, I mean, this is theta is from some pure QCD kind of property, but this has to do with, you know, the Yuga mass matrix. So now this the anomaly term is a combination of theta value and then the phase in the quark mass matrix, which is nothing but argument determinant of the quark masses.
You introduced the phase. So you introduced 5 consideration for Q very knowledge. But your 5 can be introduced for each flavor. 0.
That's right. For each flavor.
So I mean, you can introduce different files for different flavor. Then I guess in your homework, the theta is changing into the theta plus not just NF times 5, but the summation of all different files. Is it correct?
Yeah, actually, yeah, that's right. Yeah, argument determinant is actually summation of all the, yeah. So yeah, my argument was to simplify it. Thank you very much. Okay, so now this is theta bar. So what is the value of theta bar? So this is, this constitutes so-called the strong CP problem. I mean, you know, this is in terms of field strength, this is E dot B term, which is violating CP and T, or P and T basically. So, I mean, this is called the CP violating term. Now, let's do a little manipulation again. So now we rotate back this theta bar to the quark masses, quark field. Since we are talking about the effective theory of quarks in terms of meson and baryons, so this theta bar can be rotated away to UDS field by taking this okay, so Q stands for UDS. For each UDS, we assign some phase, alpha U, alpha D, alpha S. Then summing them all, okay, this is what you mentioned. Thank you. So summing them all, I mean, we can remove this operator, right? I mean, meaning we can have theta bar going to 0. But this effect appears somewhere else. So of course, it appears in the quark mass, the diagonal quark mass matrix like this. And then assuming alpha, small alpha, I mean, it has, you know, in relation to ordinary quark mass matrix, quark mass terms, we can have gamma 5 term, which is, this is a CP even, this is CP odd. So thus, therefore, we should have CP widening effect somewhere. Now, how to determine this individual alpha? So theta bar in GG dual term is basically a flavor independent term. So it sounds reasonable to assume that the theta bar flavor blindness of theta bar. So this effect should be also flavor blind. So meaning that alpha Q, MQ, alpha U, MU, alpha D, MD, alpha S, MS is the same, which we call M bar. And then, of course, we have to rotate away theta bar by like this. So we impose also this condition. So, okay, so now you can solve this. M bar goes like this. And then each alpha Q is given by this expression. Okay, so I mean, since MS is much heavier than the others, actually, most cases we will write this as this combination. I mean, this is a very good approximation. So instead of this lengthy expression, we just use this. So now, okay, so usual quark mass terms, and then CP violating gamma 5 term like this. So non-vanishing theta bar, if theta bar is order 1, we can have a large CP violation effect. Now, this theta bottom actually can induce neutron EDM. So we wrote down pi to pp or pi to nn, pi 0 to pp and pi 0 nn effective operator. Now pi plus minus should couple to proton and neutron. So it had, I mean, we had to say some coefficient j over f of pi. And then the theta bottom appears here. So it is not an easy task to see how this neutron EDM appears from this. I mean, you can look at Kim and Karoshi and other references and the references therein. And then we get, you can calculate the neutron EDM like this. So neutron EDM should be non-zero with non-vanishing theta bar. But in experiment, we found that the neutron EDM must be smaller than 10 to minus 26 E times centimeter. So from this, we learned that the theta bar should be smaller than 10 to minus 10. So why theta bar should be small? I mean, this is a gauge invariant parameter in your Lagrangian. And then it can be order 1, right? Now, this small number should be, I mean, we have to understand why this theta bar should be so small. So in particular, this theta bar is combination of the QCD vacuum and then the non-trivial phases in the quark mass matrices, which may be related to the CKM phase in the quark mass matrix, which is order 1 compared to this small number 10 to minus 10. So this is called the strong CP problem. Can you understand theta bar so small? Okay, so now we can think of various ways of circumvent this problem. Simplest attitude. Okay, so it's given by God. right? Well, or from time to time, I mean, there has been a claim that probably theta vacuum is not the real. So, I mean, somehow we misunderstood the QCD vacuum structure. Also, some years ago, there was one appeared series paper claiming, having this kind of a claim. But in this case, then how to understand the U1A problem? I mean, so then we need to understand U1A problem. And another interesting idea is that probably CP is conserved in the beginning, but it's broken spontaneously, like any other symmetries. So at tree level, the theta was vanishing, but at the loop level, it may appear. So then somehow you can make the theta parameter can be small. But assuming the initial CP conservation, then CKM phase. So naturally, you may expect that. So MA goes to diagonal like this. So alpha Q we determined. So taking rotation from the derivative term of quark field, you get also the derivative coupling of action field, physical action field, like this. And then the quark mathematics picks up, non-trivial phase contribution, which is space-time dependent. The field, action field dependent term. Now, the way we calculate the pion, kaon, and eta mass from effective Lagrangian of QCD below 1 GeV. So actually, we used this notation, this calculation. Since, so sigma, so instead of 3 by 3 mathematics, including pi k s, let's just take the pion direction only, the 2 by 2 matrix. So sigma is number ghost boson matrix. So taking only pion field. And then this mass is breaking this left and right chiral rotation explicitly. But this combination, m times sigma dagger plus summation conjugate, and then take trace. So this is invariant under, say, now in this case, SU2L cross SU2R, right? So this is the invariant Lagrangian, so that you get now you calculate this. So m sigma dagger, so should have this expression. So alpha u, alpha d we determined like this. And then taking, so this you get, from this you get this kind of expression. And this was the origin of calculating pion mass, right? So taking the second derivative of pion, you get so mu plus md times b is the pion mass. Oh, this is just a fitting parameter. Yes, so we don't know what b was. But from this, so from this m pi, is go like this, right? And then we know the pion mass. And then we know the quark masses, which is around, I don't know, 3-4 MeV. Then you get this value, which is about 400, 500, 400, 500, yeah, 400 MeV. Now K-on. So, okay, so you extend this to 3 by 3 matrix, including pi-on, K-on, and eta. So K-on mass squared goes like B times ms plus, I don't know, some mu minus md or whatever. So I just ignore this small contribution. So ms was what? 100 MeV? Yeah. Then you plug in the same number, then you reproduce measured K-on mass. The same story for S, the eta. So this was the success of this kind of effective field theory of QCD, which is called chiral perturbation theory. Okay, now I use the same technique, including the action. So what we did is that we rotate away the glue-glue dual effect to the quark field, and then repeated the same chiral perturbation theory, including actions. I mean, this is action field. Now we have the potential for the action. So then you can, actually this is the potential for the action field, and then you can get masses of action, and then you can find the minimum of action field. I already said that the A prime is the physical field. Taking the first derivative of A prime in alpha u, alpha d, I should get vanishing vacuum extent value, meaning that this should be vanishing, which I took before. And then from the second order terms, you get, I mean, we already calculated this. And then action mass also is trivial to calculate. So, so you expand this and take the second order term of A prime. And then this should be the actual mass. So FA is a so-called the Petrarch symmetry breaking scale or action decay constant, which is model dependent. I mean, it depends on how you realize Petrarch symmetry in your new physics Lagrangian. And then CA also depends on the model, but the rest we know. So from this, also you can realize that if you take mu to be 0, then action mass vanishes. So this also confirms that in the massless UCOC, we can solve the strong CP problem. So yeah, this is the one of the master formula in action physics. Okay, so now I think it's a good time to now. So tomorrow we'll talk about specific action models, how to realize, how to get CA, FA depending on the models, and then some interesting stories. Probably tomorrow I can finish in 30 minutes. Okay. Thank you.
Thank you very much.
So for the details, I refer the lectures by Professor Takahashi tomorrow and the day after. So I guess also he will talk about more about how to detect actions. So for instance, actions can be produced in the sun, like in the, from these processes, and then so we have strong magnetic field prepared. Then A times E dot B interaction, so action can convert to photons. And then the photon wavelength frequency should be same as the energy of action or mass of the action. So actions coming from the sun, this is typically keV range. if action is dark matter, floating around us and then meeting strong magnetic field, then it can convert to 10 micro electron volt. For instance, if action mass 10 micro electron volt photons. So I mean, so this kind of searches are going on. So we can actually try to observe the presence, I mean, the action field. Okay, now that so that was my final slide yesterday, and then I spent 30 minutes now, and then I knew that my lecture note was too short, so I expanded it. Okay, action dark matter. So initially, I thought that okay, I leave with that, leave this as an exercise to you, but I did it myself a little bit. So basically, this was the formula I wrote. Didn't write any details. So the action dark matter can be calculated like this. So theta is the initial amplitude of action field. And then FA is, action decay constant. So for 10 to 12 GeV, with this funny number, funny power, if theta initial amplitude of action is around 1, then actually you can produce right amount of dark matter, axionic dark matter. So you don't want to be too large, so that puts actually upper bound on the action decay constant. So lower bound basically from star cooling and upper bound from dark matter relic density. Of course, it has a freedom of how you choose the value of theta, but generally speaking, this is called the classic action window. So let's talk about how we obtain this kind of formula. So then if you have any questions so far.
You understand that bound. So the lower bound is kind of general if this is the bound if we are not considered action as dark matter. But
this is independent of, yeah.
Yeah, so but upper bound is if we think this.
Exactly,
Okay.
exactly. Good, thank you. Yeah, if you don't want action to be dark matter candidate, you throw it away. For instance, if you think of ALP in general, so FA can go to, I don't know, 10 to 18 GeV.
I mean, so if action is not the whole dark matter, then are you saying that you can just remove this?
Yeah. There may come another bound, I don't know. Yeah, basically, yes. Yeah. Okay. So misaligned mechanism is the key to produce this light boson dark matter. I mean, we already learned about it from Professor Kolb's lecture. So let me briefly repeat again. So in the expanding universe, any scalar field, neglecting higher order interaction terms here, basically this more precise, this must be the derivative action field, but assuming the higher order terms are not very relevant. So we have this simple equation to solve. So now A is not quantum field, is the classical field amplitude. And then we assume it to be homogeneous. And then it has only time dependence. So it evolves in the expanding universe like this. So this is a Hubble parameter in the radiation domination era. It's 1/T. And then it's proportional to temperature squared, right? Then when H is much larger than MA, you can forget about this. Then A dot equals to 0 is a solution. So A is constant. So this is a huge friction. So if you start from the constant A, it stays. But if H is much smaller than MA, you forget about this term. And then this is harmonic oscillator. So you have two solutions. Depending on the initial condition you put, you can determine the coefficient of appearing in front of these two harmonics. In general, I mean, the solution, the complete solution of this is Bessel functions, as we learned this morning. So again, I mean, this picture also Professor Kolb showed. So let's start with some initial amplitude of A, and then assuming the initial velocity A dot is vanishing, then around MA, so it starts to oscillate. So A goes like this, and then A prime, A dot also start to oscillate. So we have this kind of behavior. And then the energy, then from this, we get energy density behaving like this. So here I just showed rho A, the energy density divided by temperature cubed. So at the infinite time, energy density is proportional to temperature cubed, just like a matter energy density, right? So now, well, this is then, so if you assign some initial value A1, say A0 or A1 here, some appropriate value, and depending on the mass, and actually you can produce the right amount of action energy density. And I mean, this is according to any scalar field. Any ultralight scalar field can produce right dark matter density through this kind of misaligned mechanism. Probably this is the only mechanism, probably not only, but anyway, this is only a simplest and plausible mechanism to produce a huge population of ultralight boson dark matter. Now, in the QCD case, the story is a little more complicated than that. So here, for this, I am just basically copying the Bible of Kolb and Turner. If you go to the book of Kolb and Turner, you can find this formulae. So let me go through some, this action misalignment pages of this book. Now, so instead of A, I write down theta normalized by FA. So it's an angular variable, of course. It's residing between 0 and 2 pi. But before QCD phase transition, there was no potential for the action, right? So after Petchykin symmetry breaking, there is a phase field which can have arbitrary value between 0 and 2 pi. Now, QCD condensate, after QCD phase transition, so the potential develops, which we wrote before, right? So through meson dynamics, we wrote down the action potential. So that means that the subtlety comes around because this phase transition is temperature dependent. So, so in summary, this action mass is temperature dependent. And then we know that it roughly behaves like this. For the temperature higher than lambda QCD, the temperature dependence is like this. Of course, this precise value like this and these two values should be determined by some serious and exact calculations. But this is the value appearing in old textbook, like Kolb and Turner. But recently, I mean, there may be some more refined determination of these coefficients and this index. But it doesn't matter for us. So I mean, we keep this as a reference value for our calculation. And then of course, T smaller than lambda QCD, we are back to the vacuum value of the action mass. So then the action potential is again this form. So this is the form, okay, so actually that was at zero temperature, it was like f of pi squared, m pi squared, and mu, md, mu plus md, and then anomaly coefficient squared, okay. So well, in general, action model, so this becomes, we can always write this in terms of decay constant action mass. By the way, the QCD scale which I am talking about is this one, the UU bar, DD bar, SS bar condensate value. So this is dimension 3. So this QCD scale is related to our previous effective action description of mesons. So there we had this kind of expression, f pi squared b times b parameter. So from this we determine the pion mass, kaon mass, etc. So identifying these two, I mean, we get the lambda QCD around 200 MeV. Also, depending on your serious calculations, it may change. It's maybe 230, 250, I don't know. But yeah, around 200 MeV. Then again, the theta evolution equation in the expanding universe. Now, okay, so this behavior we know is h as a function of the temperature is proportional to t squared, and then ma squared t has this complicated expression. So the evolution is like this. So T much larger at a very early temperature, there was no QCD condensation, so no potential for the action. So after Petrarchin symmetry breaking, action can sit any value between 0 and 2 pi. So let's put that some initial value denoted by theta 1. Around the QCD condensation scale, until the H becomes the mass itself, action mass itself, this initial theta value is frozen at the same value, right? So we define temperature T1 where this condition satisfies. Which is nothing but this expression. So this is the temperature-dependent action mass. This is Hubble parameter. And then from this, you can determine what T1 is, right? So T1, so basically, T1 is proportional to MA to the 0.18. Which is a fun value as an exponent. At this temperature, actually, we can calculate the number density of this action field, which must be the energy density divided by the mass at that time, at that temperature, which is nothing but this one. And then you get the so-called Y number. So number density divided by entropy density at that temperature. So this is the conserved quantity, right? So now you can determine all these quantities, and then now we can get the final Langmuir density of action in this way. So omega value is the action number density at present divided by critical density, and then the action energy density is the mass times number density. So this initial number density normalized by entropy density was determined through these equations, through this process. And then the current number density is this number times current entropy density. So, okay, so you do all the calculation, then yeah, roughly, okay, from this we already have this kind of behavior. So this whole quantity is proportional to the mass itself coming from this, and then FA squared coming from somewhere, and then 1 over T1 coming from this, and then MA, T1 you determine from this, and then MA is proportional to 1 over FA, then at the end of the day, this whole quantity is proportional to FA to the 1.18. This is the fun number you can calculate. So then we can get a more precise value for action number density like this. So now the current dark matter density should satisfy this number, and then depending on the lambda QCD value you put, although I didn't talk about this, so you can get this expression. And then also depends on the initially frozen value of theta, and then yeah, like this. So now the action was introduced to solve a strong CP problem. I mean, probably this is the best solution to Pechakin, the strong CP problem. Then we realized that, okay, this action condensate action, classical action field can be a dark matter candidate of the universe. So we get it free. So that was why action was very popular all days. And then this kind of structure understood for a long time. And then people were not interested anymore. But now since, you know, no supersymmetry, no dark matter, no WIMP, so actions and action-like particles became again very popular. So now, I mean, when I, as a PhD student, I studied this kind of structure. And at that time, I mean, I didn't expect to have such many experiments probing actions and then action-like particles. So when I first heard about action-like particles, then, oh my God. So, you know, action-like particle meaning that you assume arbitrary value of FA, arbitrary mass of A, and then it may not have QCD anomaly, but it may couple to A to gamma gamma. So coupling the action or ALP to gamma gamma is a good place to look for. So now, I mean, in this review article, feebly interacting particles, I guess. So they update this review article every year. So this is most recent version. So I took this from 2023 version. So here basically, you know, globular cluster solar neutrino. Okay, so it's a solar neutrino. It's a keV energy solar neutrino probe. So you get we put the bound this coupling. Okay, so I mean the classic. Okay, so the standard normalization of the coupling is like this. So it has this inverse GeV dimension. So so this is you know the Starkling bound I mentioned, and then the ADMX is the experiment probing dark matter action. So the standard QCD action window is around here. So actually, this corresponds to FA around the 10 to 12 GeV. So this window is the invisible action window. Both the KSVG and DFSG window. And then ADMX is probing this area. And then the plan is to cover around here. But the higher mass region is hard to probe. So, but yeah, there are many suggestions to probe this, but I'm not sure whether in the future we can reach down to this lower limit of DFSG or KSVG action. And then Korea, as you know, we have CAP. Unfortunately, I didn't superimpose the CAP sensitivity, but somewhere around here, I guess. Also, ultralight action-like particles, in particular probed by Dangmero radio experiment. I mean, okay, so it's impressive to see how sensitive it can be. And then, of course, the higher mass ALP is X-ray range. So if it actually the case, we should be able to observe these X-rays from the sky. So this is the bound, the current bound, and then future proposals. So all these, yeah, all these are current bound, and then the faint curves are future sensitivities. Okay, so the reason I show this is that is to advertise my own paper. So we sort of one funny action-like particle candidate. So we assume Zn flavor symmetry, explaining it's like a Frogat-Nielsen mechanism, explaining quark and lepton mass hierarchies. So instead of U1, we introduce Zn. Since we have only Zn, we can have Zn invariant potential for the flavon field, the complex flavon field. So the phase field of a flavon field can be, you know, exactly action-like particle. So depending on number of Zn, you can have different FA and different mass. So this is the line we are having in this particular type of action-like model. So then, you know, I mean, still long way to go to this. So we need to fill in this area to prove this kind of model. Probably we see some signal around here or around here. I mean, here it's interesting that it matches standard QCD action-like particle prediction. So of course, I have shown only my own model, but there could be a lot of different models you can have. Yeah. So, and then in the future, we may be able to see some signals somewhere, hopefully. Okay, so that's it. Thank you.